Good morning, everyone. Welcome to the today's first session by our beloved professor from JNTU Hyderabad, Satya Savithri ma'am. Ma'am, I welcome our HOD ma'am to give the bouquet. And take, now name of please take introduce.
Good morning, all. A warm welcome to the second day movement session of our daily. A warm welcome to today's speaker, Dr. T Satya Savithri ma'am, Professor, Department of Electronics and Communication Engineering, JNTU Hyderabad. Ma'am has completed BTech from REC Warangal Kakatiya University, MTech College of Engineering in Usmania University, and PhD Department of Electronics and Communication Engineering, JNTU. Ma'am has organized 20 workshops and attended 30 workshops, and ma'am has more than 30 years experience in teaching and research activities. Ma'am has guided 13 research scholars and authored 54 international journals and 44 conferences. Ma'am has vast experience in signal and image processing. And ma'am is also one of the member of recruitment committees of DRDO and recruitment board member of lectures in polytechnics and member of studies board of governing body of affiliated colleges and so on. And a warm welcome to the today's session, ma'am. Thank you.
Good morning, all of you. Since mic is not necessary, I think very few are there. So let's start the session. We are going to be cover in this session the Wavelet transforms and image fusion and how Wavelet transforms are using for the image fusion. I think last yesterday's image might be know the fundamentals of image fusion. Where we were going to be see what is the Wavelet transform, how it is useful to do image fusion. So let's consider what is actually the wavelet. So if you are see the dictionary meaning of the wavelet is a small wave, and Wikipedia has defined as that a wavelet is a mathematical function used to divide a given function or continuous time signal into different scale of components. Suppose if you are consider any signal processing theories, basically it has to be came from the fundamentally we can say that a four things. One is based on the orthogonality, that is in a fundamental principle. So if you are considered based on orthogonality, whatever you come across the Fourier series, Fourier transforms, from that a Laplace transform and Z transforms and so on. So if you are, for example, if you are say that a function is represented in terms of a DC component and a sinusoidal components is the Fourier series. So in that way, here also the function is expressed in terms of different scale of components. So we call that exponential function. If you are considering the Fourier transform, it is called as a kernels, forward kernel and a inverse kernels or a reverse kernel. So here it is not fixed any kernel. So we have to be consider any function that has to be represented in terms of the wavelets. That wavelet may be anything. Okay, we are not defining wavelet, and that is not considered any input like exponential function is expressed in Fourier transform. And if you see the function represented Fourier series, sine, cos, and DC component, then here also we have to be choose as in a different functions. And whatever the given function is there, that has to be expressed in terms of these related wavelet functions. So that will be called as a wavelet. Whatever we are consider a function, in terms of that, we are expressing the given function. Those are called as the wavelets. So to apply the like how function has to be act like an wavelet, there should be satisfy certain conditions. We are going to be seeing what conditions is required. So the first theory is based on the basis functions is an orthogonal functions. Whatever the Fourier transforms is applied or developed. Actually, we are starting the definition of the transforms onwards, but how they are defined, why they are defined like that, we didn't come across. So if you are seeing fundamental mathematics, in the mathematics, based on the orthogonality, these transforms are exist. And like that, another analysis is present called as a multi-resolution analysis. And cover that slightly the multi-resolution analysis also. So that is the basic thing to develop this wavelet transforms. So based on the multi-resolution analysis, the wavelet transforms is actually the derived. That is one of the theory. Another theory is also there based on the filters. So you can also choose your own wavelets according to the applications. So while the explanation, it is going to be see how we are going to be generate the wavelet transforms and what is the applications. Okay, one of the application only the image fusion, like that many applications is there. Not only ECE people using for the signal processing, even civil engineering also is used to find out cracks in the walls or structures and the texture of the structure, like that they are also applying the wavelet transforms. So application of wavelet transforms is so many are there, but to generate the wavelet transform is a very difficult. How to choose a fundamental wavelet function. So what the meaning of this definition or the meaning is giving that any function can be expressed in terms of a scaling components, different scaling components. So what component we are going to be expressed, we will see that. So this will be, you can say, it is a mathematical technique in which particular signal is analyzed in time domain using a different versions of translated and dilated basis functions. So if you are considering a Fourier transform, it is expressed that a t has to be expressed in terms of frequency. As in signal processing, we are using the time domain conversion into a frequency domain. But as in a mathematical point of view, you have to be considered that a one variable is represented in terms of the other variable. In the signal processing, we are considering that as a time and frequency. Like that, we can go for any parameter. It is not exactly that always the time domain is converting it to a frequency domain. It is the in point of view of the transform, one variable is represented in terms of the other variable. So if you are consider any transform, just like a logarithm, okay, if you are using the logarithm to apply, a range has to be reduced. Because of that only we are applying the logarithm. For example, if you are say 100, so it is we can represent as in 2. Suppose if you want to represent in terms of a generalized values, it's varying from a 1 to 100, you require in a large axis. So instead of that, if you are applying the logarithm on that, it is going to be its range is reduced. It is from 1 to 2. So in that way, so 0 to 2. So in that way, here we are going to be using the transforms and it is represented in another form in such a way that convenience, according to our convenience, depending on application, we are representing in a convenient manner and apply your requirement. That is the fundamental necessity of the transforms. So convert the signal into a series of wavelets. I already given an example that a Fourier series, if you are considering, it is going to be expressing like a A1 cos t, A2 cos 2t like that. Here also we are going to be given as a series of wavelets. And provide a way for analyzing waveforms bounded in both frequency and duration. Okay, in signal point of view, I'm talking about that the frequency and duration. So if you are considering the wavelet transform, generally a single parameter has to be transformed into any two parameters. In the signal processing, we are considering that a time t after the input variable is represented in terms of the two other variables a and b. And a and b is the integers. It is not talking about frequency or time or space like that. A and b, the two parameters has to be defined according to the application. So for the fundamental input t is converted into an output a and b parameters. So that is the representation we are seeing here. And can vary in scale and conserve the energy while computing functional energy. This is talking about that if you are using the wavelet transform, you are going to be compress a lot. So in terms of energy, it is going to be give as a more compression. In that way, we are using the wavelet transform. And we have to be keep in mind that just applying the transform, it doesn't do anything. We have representation is changing, that's all. And after representation change, you are applying the certain rules on that according to your requirement. That rules has to be defined properly in such a way that it has to give a more benefit. Just applying the transform, it doesn't do anything. We are just changing the representation only. So that representation may be according to our requirement. Based on that, we are going to be doing certain things. So basis functions are localized in frequency. Okay, here in signal processing point of view, I'm saying that it is localized in terms of the frequency. So if you are seeing, I'm just mentioning a very few advantages why we have to be go for the wavelet transforms. So it is well suited for approximating data with the short discontinuities. If you are go for a Fourier transform or a Fourier series, it is a difficult if there is a short discontinuities are present and it is not going to be represent those discontinuities. If you are go for the wavelet transform, we can able to represent it. And for example, I am also showing that what is the meaning of that discontinuities. And allow signals to be stored more efficiently than the Fourier transform because it is going to be given as a more energy compaction. And accurately deconstructing and reconstructing fine non-periodic stationary signals. This is very important to apply for a real world signals. If you are seeing any real world signals, they may be a non-periodic and non-stationary signals. So if you do for a real-time signal processing, better we go for a wavelet transforms. And can extract a local spectral and temporal information simultaneously. This is talking about especially the spatial variations. Wherever like image processing, if you are consider any spatial variations is there, for that you can go for a local spectral in the sense a part of the spectral itself we can able to process it. Once you apply the wavelet transform, you can go for any particular part in the amount of the entire part. If you go for a Fourier transform, you have to apply for all the period, whatever is applied for entire period, we have to be talking about, and entire period has to be processed. Instead of that, you can go for any local spectral and temporal information. That is, if you are choose a certain part of it and apply any processing of that independent of the other things. That is the major advantage if you are go for the wavelet transform. And after multi-resolution analysis, by capturing the localized features. Okay, if we are saying that instead of the global wise transformation, we can go for a localized. The above one and below one is mostly the same, but if you are talking about in the frequency spectrum is the third one. Based on multi-resolution analysis, we are saying that a second one. Okay, and being able to better approximate real world signals. I already said that. So this is a clear understanding of how to represent it. So if you are considering a first one, it is a time representation, right? So if you are seeing x-axis is time and y-axis is the frequency. So if you are varying the time and giving as the frequency is fixed, so that is a time domain representation. And next one is the frequency domain representation. Frequency y-axis is varying, x-axis is not varying. So it is a frequency domain representation. After these two things, before of the wavelet transform, we come across the short time Fourier transform. So you have to be choose as a like a window of this structure. On that window, again apply the Fourier transform like that for the entire period of the signal. We are applying the Fourier transform by choosing the different fixed length of the window. So if you are consider that x-axis and y-axis both will be varying, time and frequency resolution is of time, but it is in a fixed slots. So for the entire period, we have to be choose as a fixed window length. Whereas in the wavelet transform, we can change that length of the window. So x-axis and y-axis, if you are consider frequency and time, it is going to be given as a resolution both time resolution as well as the frequency resolution is of time. So that will be the clear understanding of why we have to be go for the wavelet transform. It is providing both time resolution as well as the frequency resolution. So this will be the meaning of that. Okay, if you are go for a short time Fourier transform, the window length we cannot change. It must be a fixed, independent of the requirement. Here we can able to change the window. So window may be represented as anything. Here I have drawn as a rectangular window. But you can go for anything, window in the place of the window, you can go a small wavelet. That wavelet is maybe any function. So if you are consider the window must be a narrow windows, it is more appropriate for a high frequencies. Whereas if you are go for a wider windows, it is for a low frequencies. Just I am giving us a three different frequency signals. How we are going to be choose as a window, based on that we can able to represent that signal with a different resolutions. So if you are go for a single as a frequency of signal, there will be a three frequencies, three variables is there. So if you are representing that in terms of a common thing, it is a difficult because in signal itself is varying as a three frequencies are there. So if you are go and represent with respect to the wavelet transform, different resolutions can be introduced in the same signal. So generally, wavelet transforms is also fundamentally divided types. We can say it is a continuous and discrete wavelet transforms because the mathematical way, whatever is already expressed, it is the same thing. Okay, how the developments is done in the same way. How Fourier transform is varied in the same way. Here also, depending upon the input signal, we have to be choose either a continuous wavelet transform or a discrete wavelet transform. In addition to that, there will be any other wavelet transforms also there, called as the wavelet packets, biorthogonal wavelet transforms, and multi-wavelets. Okay, and we are going to be seeing first two only. And if you say that the wavelet packets, it is also a more or less same of the wavelet transforms only. But one thing here we are considering is that a slight difference is there. If you are seeing a continuous general wavelet transform, while explaining, I will give it. Okay, what is the actual difference with respect to the wavelet packets and general wavelets and biorthogonal wavelets in the specific case? Okay, whenever if you are saying the signals is a orthogonal, I started with the classes that orthogonal basis, orthogonal functions. If the two functions are satisfying orthogonality, there will be a lot of advantages are there. But practically, if you are observed that all the signals or all the functions may not be satisfied this orthogonality. By that case, we have to be go for it biorthogonal. As a pair, okay, if you are say A1 and A2 are two vectors which are not satisfying the orthogonality, then we have to be develop another pair respectively from these vectors called let's say B1 and B2. So as a pair, A1, A2, B1 satisfying the orthogonality. Once we are calling that as a pair satisfying orthogonality, we can apply all the mathematics on that. So for that purpose, orthogonal, biorthogonal wavelets are developed. And in the multi-wavelets, actually we are saying the multi-resolution analysis based on that these wavelet transforms are developed. So if you are considered with respect to that, the wavelets, whatever we are considered, there will be a function called as a scaling function. Okay, from the scaling function, we are going to be see the wavelets. So that scaling function, instead of taking as a single wavelet scaling function, that function is divided to a small parts, and that parts is applied. Remaining theory is the same. So that is called as a multi-wavelets. So advantage is going to become if you are go for other types, okay, with the wavelet packets or in a multi-wavelets is that it is going to be you as a less amount of hardware is required. For that purpose, generally those two wave transforms are developed and it is an advantage in terms of that. So these are the certain examples. Okay, we are saying that wavelets, right? So depending on the certain requirement, they are developed. These are the wavelets. So there is a fundamental rules. I will give you next slide. If the rules are satisfied, we can call that as a wavelet. But these already developed wavelets is already used for certain applications. So we can say Mexican hand wavelet. It is given mathematical equation is that, and certain wavelets is developed randomly, and it is given as a values. I can say radio broadcasting, they are applied wavelet transforms and they are used like in numbers. But the case of the inputs, it is going to be given as the output. So they defined the wavelet is in terms of a particular specific application and use it like a wavelet transforms. So like that, it is for a particular applications they are developed it, we can able to give the mathematical equation. So sometimes we are not able to give a mathematical equations for the wavelets and algorithms is there to develop the wavelet coefficients. So like that, the Wavelet is one of the wavelet, and Wavelet is the name of the inventor. So Wavelet is given one algorithm. So according to that algorithm, we can generate the coefficients. That is one of the theory. Okay, I am not covering that theory. Other based MRD analysis based on that how the wavelet transforms are developed only I am covering here. So like that, there will be a lifting scheme is also there. So based on that, also we can develop the generate the wavelet coefficients. So these are certain examples and there is a no particular shape or a particular interval. Even we are seeing the equation by these three are explained and certain wavelets doesn't have an equation also. So only I'm saying that these are the some developed wavelets already used. So generally psi of t is called as an a wavelet. So whatever we are using in the wavelet transform, the wavelet function called the mother wavelet. And I'm saying that no, any function can be used as a wavelet, but it has to be satisfy certain conditions. These are the conditions, that is, it must be an integrable. So gives as an oscillatory condition. And second condition is that it must be a square integral. So whatever till now you have used in the signal processing, whatever the expressions, unit step function, impulse, or exponential ramp, whatever may be, these two are always there in the signal processing. Okay, whatever we are using the functions, it has to be integrable and it has to be square integrable. The meaning of thing is that first equation is saying that the existence, and second one is saying that it contains some energy. If you are not giving these two functions, it is a meaningless because there should be existency must be there, signal must exist and it contains some energy. So whatever you are considered, all the signals has to be satisfied these two. So if you are see some standard books, they will be give as a some function f of x lies in L square, double curved L will be there, L square of that L square is indicating that a square integrable energy. Okay, if you are see very fundamental books, standard books, always the sums is given that the function belonging to the group L square of that, then only it will be satisfied. So these two is always there and for wavelets also this has to be satisfied. And there is another condition called as an admissibility condition, and this condition is given in terms of that inverse transform has to be come. Once we want to use as a term transform, in the forward direction, whatever you are transformed, you have to be reconstruct as it is. Then only we can call it as a transform. Otherwise, if any loss is there, it is not at all a transform. So the fundamental requirement is that forward conversion, and again it has to be get back. Third condition must be satisfied. So whatever you are choosing as a function, work as a wavelet function, it has to be satisfied these three conditions. And psi of omega is it's a Fourier transform. Psi of t you are called as a mother wavelet. Psi of omega is a Fourier transform of it. And the definitions is proved. Inverse is that inverse Fourier transform is a true. Then inverse Wavelet transform is also in a true. Based on that, it is developed. So these three conditions is required to work any function as a wavelet. Whatever we see in the last slide, the functions, whatever we are given. These three, if you are see that all these three conditions is satisfied with respect to these equations. It must be an integrable, square integrable, and satisfy the admissibility property. So if any function is satisfied, you also take that function and do the wavelet transform. So this will be the definition of the continuous wavelet transform. So it is given as that the given function is the f of t, that t is transferred in the output variables is a and b, and psi conjugate t minus b by a is with respect to the mother wavelet function psi of t. Next slide, I show what is the relation between of psi of t and psi of t minus b by a. So this is the definition of the wavelet transforms. Almost transforms are defined, not the derived. Based on a certain fundamental concepts, they are defined. So this is a continuous wavelet transform where A is the scaling factor and B is the translation factor. So this is an effect of scaling, that A parameter is called as a scaling parameter and B is called the translation parameter. So the given time variable T is converted into a parameters A and B. A is the scaling parameter, B is the translation parameter. So effect of the A, if you have observed, I am saying that first one is the A is at a 0.5, second one is a 1, third one is 2. If you are see, it is energy is widened from lower value to the higher value. That is the effect of the scaling. X-axis I am taken as the time and Y is the amplitude. So with respect to that, if you have observed, if you have got increase in the scaling, the energy is distributed more. So any function, this is Marlet wavelet, effect on the Marlet wavelet, if you are increasing the scaling factor, the energy is distributed on time scale is the more. If you are seeing the distribution with the effect of frequency domain, okay, if you are taken as the above figures is the time domain, if you are finding the frequency domain, if you are see the narrow of that lobe is decreasing. That means if you are widen the time, frequency has to be reduced, right? So that is satisfied here. So if you are given as that a time, the left side figures is the original figures. If you are increasing the scaling parameter, the frequency is going to be narrower, time is elaborated. So the fundamental definition here, it is satisfying. By that we can say whatever we have taken as a definition of the continuous wavelet transform, it is a true. So frequency resolution is increasing, time resolution is decreasing. So if you are, for example, if you are taking as a sin t, if you are taken as a scaling factor at a equals to 1, f of t is given as a sin t. Then if you are given as a scaling factor, here I am taken as a reducing a. So a is half, then sine of 2t, if you are draw that. And if a is at 1 by 4, sine 4t. The resolution and time parameters are inversely proportional. In the wavelet transforms also, if you are changing the scaling factor, it is going to be given the same effect. So this is a scaling factor with respect to the Wavelet wavelet. So if you are considered that the values of the A, filter has, if you are talking about in terms of the filters, so filter has a frequency response centered at a low frequency value, and therefore the corresponding wavelet transform is seen as a function of B for a fixed A captures the frequency content of f of t around this low frequency. Okay. If you are taken as the large values of A is increasing means frequency is getting narrower to the center, right? And smaller value of A. If you say that the band pass shifts to a higher frequency, implying that the PWT at a small scale contain information about f of t at the higher end of its frequency spectrum. So if you are born smaller the values, it's going to be elaborate in terms of the frequency. As I increase the frequency response, shifts to the lower end of the spectrum with corresponding to the shrinking of the bandwidth to maintain the constant Q factor. Why we are discussing all these things is we are saying that whatever the definition is given for the wavelet transform, it is satisfying already whatever you have known. So if you are saying constant Q factor has to be maintained the bandwidth gain product. So that must be in a constant. So if your see time is increasing means frequency is reducing. Frequency is increasing means time is reducing. Depending on that, you are choosing the values of the A. So it is satisfying whatever is already existing here. And translation parameter B is affects only on the location of the wavelet, not duration of the bandwidth. So where this bandwidth, entire bandwidth has to be located, that is talk about only the B. So B is only the shifting parameter. Suppose if you are defining any function at a t, B is talk about that this function has to be obtained at a t minus B or t plus B. Location is talk about that. The duration t doesn't get any effect based on the B. Okay, B is only the translation parameter. So we already defined that psi t minus a by b. So we are taking that as an psi a b of t for the simplified representation. So the wavelet transform is no f of t 1 by that is only the scaling parameter root of 1 by a and psi a b conjugate of t b. So here the definitions if you are consider, let's say a energy wise if you are consider integrable function, the total energy contained in the mother wavelet is same as psi of AB of t. That means at any integers, it is going to be due as the signal complete energy. Okay, psi of t is defined as a wavelet. So that function in the continuous wavelet kernel is taken as a psi AB of t. So if you are considering energy spectrum for the psi of t and psi AB of t, both will be the same for all the values of A and B. And if you are considering, let's say only B is in a 0, so psi of A0 of t is 1 by magnitude of A psi t by t. So that will be tuned psi by t. The law of conservation of power also. So based on these things, we can say whatever definition is given, it is going to be defining the same thing. Okay, whatever is necessary is fine. I think you may be hearing now. So another things, whatever we are defined, is it a true has to be proved based on the correlation function because this theory is already developed. So you know that the cross correlation between of the two functions is here. Inner product is defined as x of t, y of t, two functions you have taken. It is minus infinity to infinity, x of t, y conjugate of t. That is the meaning of the inner product of that. So if you are taken as a cross correlation between of two functions x and y, the definition is that and it is equivalent of x of t by t minus t. This is already developed correlation function, such as well proved. And if you see the definition of continuous wavelet transform, and f of t is given function, psi abt is your wavelet function. So if you are take those inner product of those things, it is same as the correlation, cross correlation between of the two functions. So it is also representing as a cross correlation between of the two functions. Till now, what we have said that the function is expressed in terms of the wavelet functions, right? So here we are proving that similarity between of taking the two functions is based on the cross correlation. So whatever the equation is developed, it is also true if you are defining like that CW. So we are proving that the definition, whatever is given, it is in a true based on the correlation function also, it is in a satisfied. Okay, if you are defined the Fourier transform, it has to be proved in such a way that it has to be came from the fundamental orthogonality principle. So if you are considering the forward direction exponential plus j, in the inverse direction exponential of minus j. So if you are multiplying those two, the overall effect is nullified. So that is the basic requirement, and based on that, that is defined. Here also we try to defining that existing theories has to be satisfied, whatever the equation is given. So another concept is based on the filter theory. So if you are consider that x of t is an input and ht is an impulse response, then if you are say filter operation is the convolution of those two. So based on this theory, CWT is also defined in the same way. So if you are consider the WAB equation fundamental, if you are see f of b is convolved with a psi a0 of t. So in the filter theory concepts also, whatever we are defining the wavelet transform equation, it is in a well satisfied, and whatever definition is there, it is in a true. So based on these two theories, we are saying that whatever the definition is given for WAB, it is a valid one. One example we will see, because definition wise we are given why this wavelet transform is getting that much of significance. Now we can understand from this example. Okay, I am said that wavelet must be a certain function. So here I am taken as that wavelet is in a hard wavelet. Okay, that name is given as a hard wavelet. So psi of t is 1. That intervals, okay, you are taken as -1 for half to 1, and you have to be find the CWT for the given function f of t is 1. Just simply we are taken as the given function is a 1 in the interval 0 to 1. So for this given function, psi of ABT has to be converted, because I said A and B have an integer value. So there will be any limits we have to be defined. So initially we assume that A is greater than 0. With respect to that, the time parameter has to be given as the limits. That limits has to be changed in terms of the B. So B to T, B plus A by 2 is 1 by root A. Just to substitute psi of t in terms, that is T psi ABT. Relation I given now, psi ABT is T minus B by A is the equivalent of psi T. Last slides we have given the equivalency. We go there. That is the definition, right? Psi of ABT is 1 by root A psi of T minus B. Here we are given as psi 10 T is the psi of T. Here psi of T is given, right? The psi of T is given. We are writing the psi 10 T from that psi ABT. So that function is going to be given as the values of psi ABT. So we have to be expressed in the signal terms. We have numerical values. We cannot go in the mathematical way. Substitute in terms of the other function. So here we taken as a unit step function. Generally, we can go if any signal processing has to be do. We have to be expressed in terms of the other impulse function or a ramp, unit step, and exponential like that. So easy one is the unit step function. Generally, impulse is very much easy compared to the UT, but impulse is defined only at t equal to 0. So instead of that, better you analyze with respect to the unit step function. So we are considered that in the unit step function and given as psi ABT in terms of the unit function. Now this is the wavelet function. We have to be apply a CWT to find the function value 1. So from the definition, just f of t substituted 1, and the 1 is in the given intervals is 0 to 1. In the definition, it is minus infinity to infinity, but the given function is 0 to 1. So let's substitute those intervals. And so you are getting as the three terms of the integrating functions. So integrated, okay, based on required limits. Here limits application is important. Properly have to be applied that. So if you are considered t minus b is 1, value is the 0, other one is t minus b is a 1. What possible intervals is there? We have to be defined that intervals give the respective functions. So this will be the I2, I3. So for the value of A, we are taken as 0 to 1 and intervals is divided as minus A by 2, 0, 1 minus A by 2 less than 1. So within these intervals, we have defined the continuous wavelet transform one set, right? Here the values is taken as A is varying from 0 to 1 and the subintervals is taken as that minus A to 1. With respect to that intervals, you are given WAB, that I1 minus 2 I2 plus I3 integrated wavelet transform function. This is one of the solution. So if you are change this, taking that A is 1 to 2, and I didn't change the values. If you subintervals, if you are consider minus A2 less than 1, and this will be the other values. Okay. Previous case is one type of condition. Here is the another set of condition. And if you are consider A is greater than 2, this is the another solution. This is the requirement with respect to the wavelet transform. So you can define any values at any intervals for the given function. If you are go for a Fourier transforms or other transforms, it is give only one unique solution. Here it is not at all a unique solution. According to how you are chosen the intervals. So here the limits, whatever you are chosen, based on these conditions, the solution is varied. So depending on the applications, we have to be choose properly. That is in your hand only. The transform is not arbitrary, it is not going to be give fixed way. You have to be choose properly to get a more utilization. Your given function is only the one. Okay, it is a very simple function, but that one function is expressed in terms of the R wavelet within a different intervals, within a different solutions. So it is never give the unique solution. You have to be go. This is called as a resolutions. Multi-resolution results is going to be come. So that will be the actual solution. And if you are saying W of AB is equivalent of minus W minus A 1 minus B. This is one of the conditions that if you are not WAB, you can also get the equivalency is minus W minus A 1 minus B. And it is difficult to obtain a closed form expression. Okay. How properly you are choosing the A and B values, depending on that, your solutions is changing. Because of that, we can say it is difficult to obtain a closed form expression for the CWT, even for a simple functions. And if you see the quantity square integrable of WAB, it is called the spectrogram. How we are getting the spectrum from the Fourier transform, it is called as a scaleogram. So location of scaleogram provide information about the positions and duration of event in the original signal. So that is the more advantageous thing if you are going for the wavelet transforms. So now we talk about the multi-resolution analysis. Basically, CWT is not much useful because everything now is in a discrete way. So to apply that, especially for the image is only the digital media, or we can say it is only the discrete values. So to do that, we have to be apply the DWT only. So discrete wavelet transform fundamentally, one of the theory is this one. By based on the multi-resolution analysis, we can define that. I given the definition of CWT and proved that that is it true. Okay, now from this analysis, we are going to be take the DWT. So another analysis is there called as a Farley phase filters also. I'm discussing slightly the filters concepts also. And modeling is given fundamentally in algorithm such that it has to be developed the wavelet coefficients. And another generalized technique is called as the lifting scheme. That is a very much generalized scheme is available. So that based on these theories, we can develop the DWT coefficients. So here in the multi-resolution analysis, basic four fundamental theories I said, no, one is the orthogonality, another one is multi-resolution analysis.
the DSP generally how we are going for the vector space analysis. Separate vector calculus and vector functions set theory all will be developed based on the vector spaces. That is another analysis. And estimation and prediction theory is another analysis. These four theories are very fundamental to get any equation, whatever till now we are used. So one of these is that a vector spaces. V is the vector space. So if you are consider this region is the infinite space, everything is contained in that. So it is starting from minus infinity to plus infinity. Generally, we are taking as minus to plus no. Here it is not defined in that way. Taking as right minus infinity to plus infinity to minus infinity. So low region upper that like that it is defined. So in the vectors or set theory also we are seeing that if one area above of that. So if you are considered lowest one is called as a Hilbert space. In that if you are defining as a certain properties, it is also satisfied. It is covers if in the next region if you are say the subspace, whatever properties in the present any function in the Hilbert space is also contained in the subspace. All the properties present in the subspace is also contained in the vector space. So like that it is defined. That is called as a nested loops. So the linear vector spaces is given in that way. So whatever properties you are defining for V1 belongings to V0 means V0 is also having all the properties in the V1. According to set theory, I given one example. Let's say the elements present in the B is belongings to the A means whatever elements is present in the B, that elements is also present in the A. So in that way, it is formed as a nested vector spaces. If any function is present in that, only we can use a multi-resolution analysis because I already said that way. Everywhere we have to be talk about the curved L square. I'm saying that L square R is here R is considered as a region. Sometimes they represent as a real number also. Here it is a region. That is any function or a present in the R is a square integrable energy function. If you are add all those things, you are going to be get as a original one. Union. It is not mathematical addition. If you are combine all these subregions, you are going to be get as the overall region. That is called as a union of these subspaces in dense in the space of square integrable functions. And second is called any two areas, whatever you are dividing is in a separable areas, there will be no common element. This is useful until your neural networks. Okay, whatever we are saying that you have to be divide a subspaces between of those two subspaces, no common element will be present. That is called as a singleton means if it is a vector, it is a zero vector. You have to be given an element, zero element like that. So intersection of these subspaces is in a singleton. And if you are saying a function belongs to a vector space Vk, then f of 2 is the next level. So f of 2t belongs to the Vq minus 1 and vice versa. Okay, any function if you are considering the vector space, that if your second level f of 2t is belongs to the second level of the vector space. If you are understand what is the meaning of linear vector space, these three are related to those only. That is V1 belongs to V0 belongs to V minus 1 so on. So if you are consider f of t is belongs to the V0, f of 2t is belongs to the V minus 1. That is the meaning of the third one. So there exists a function called the scaling function phi t such that phi of t minus k, where k is any integer is basis for V0. If it satisfy any function because in the linear vector spaces, then we have to be express the type of the functions in terms of the scaling function called the phi of t. So according to the multi-resolution analysis, we can express any function in terms of the scaling function phi of t, and that function must be belonging to the linear vector spaces. This is the definitions of the environment analysis. So whatever the condition the phi of wavelet is defined, any function can work as a scaling function if it satisfies these conditions. First two is common, okay? Whatever signal theory you have any signals, first two conditions is always same. That is existence of the signal and it must contain a certain amount of energy. In addition to that, it is given as an orthogonal property, that is phi of t minus n is in a del. That is function phi of t and its translates. Phi of t minus n must be satisfied the orthogonality. So if you are considered as a sine t, sine of phi minus t is a both are orthogonal. If you go for any periodical translations, the condition is satisfies. So all sinusoidal functions will satisfy this condition. So scaling function can be worked as a sinusoidal functions. So if you go for a generalized one, next equation is given as a generalized one. So here the same thing. Whatever the phi of t you are considering, phi of t has to be satisfied. F of t belongs to the vector space Vk minus 1. So as per the multi-resolution analysis, we are choosing that phi of t to express the any given function. So phi of t is defined as C of n phi 2t minus n. Because of that, orthogonality property has to be satisfied. So if you know at any level of the function, we can define at any level by the coefficient C of n. So the function given is expressed, f of kt is expressed in terms of this with the corresponding coefficients a k. The phi scaling function has to be defined as can be generated from this one. Suppose you doesn't know anything, we have to be start that at initial value we say 0. So based on that 0, we are going on constructing it. So properly you have to be choose the value of Cn, go any iterative algorithm, then we can estimate the function of the phi of t. Generally, we have to be interpret the mathematical equation with respect to the requirement. So any function can be expressed in terms of a scaling function with a respective coefficients is taken as a. So we are defining here in two levels. F minus 1 of t, just to substitute k equals to minus 1 and k equal to 0. And we are saying that F naught t is the orthogonal projection of F minus 1t on V naught. So you are taken as F minus 1t. This function is projected in the vector space V naught, that is called as the F naught t. When we are saying the function is projecting in the other, both must be the same. But there should be a certain error. That error is called the detail function or the error function. So G naught t is F minus 1 of t minus F naught t. Based on these things only you are getting as a back propagation, forward propagation, all those algorithms is fundamentally came from this concept. So if you are say that this will be on the vector space definitions. So if you are finding that from AK and coefficients for FKT in terms of the basis for PK. So now I'm considering like that you can go for any function can be expressed in terms of the scaling function. And now giving us a relation between of the wavelet and the scaling function. So if you are consider these things, these first two equations already we have defined. In addition to that, it must be give as a orthogonality. Psi of t, psi t minus n must be orthogonal, and psi of t phi t minus n is a 0. That is the orthonormal function. So whatever we are choosing as a wavelet function, that function has to be satisfied this condition with respect to the scaling function. This is a necessary thing. So any function acts like a scaling function. Based on the scaling function, we are generating the wavelet function. Okay. So multi-resolution analysis based on that, it is said that any function can be expressed in terms of the scaling function, and wavelet theory, wavelet function is related to the scaling function is that fourth equation. So from that we can derive any wavelet functions. So now the wavelet function is expressed in terms of the scaling function is the d of n coefficients phi 2t minus n. So this is called as the two scale relations for the psi of t. And any function can be expressed in terms of scaling function plus wavelet function, and that must be equating to f naught. And you said error, no, that error is the g naught t. So this function is called the error function. From basic these things, we are generating the coefficients in terms of the given function coefficients and wavelet coefficients. So this f minus infinity is defined as bkl psi 2 minus k t minus l. This is the definition of the dwt. Right? dwt is expressed in terms of the wavelet function and respective coefficients. So any function can be expressed in terms of the wavelet function and respective coefficients. And this coefficients is generated based on the wavelet function coefficients and the given function coefficients. And this is going to be satisfying the given function. Okay, so based on this, we are defining the wavelet dwt. So now we concentrate with respect to the filters. Let's consider the filter functions h of n, g of n, h bar and g bar n are defined as filters. And from the multi-resolution analysis, whatever coefficients you are considered, this coefficients is defining a low pass filter. If you are considered here, this must be the high pass filter. If you say this is the low pass, this must be bar. So it is a period of pi. So high pass, if you are considered this as an high pass, this is a low pass. Because of that, it is given as h minus n, g minus n. Whatever the coefficients in the previous theory is defined, with respect to that, here we are giving us an equivalent filters. And these are defined filters. So if you are seeing the coefficients a, k, n, which are the coefficients related to the given function, derived at any instant of time based on this filter response and the previous values. Okay, previous values of coefficients for the given function. So AKN is obtained from AK minus n by convolving the latter with the sequence h bar n and returning only the even indexed samples. So you are generating this BKN coefficients based on the filter. Okay, here you have to be see there is a coefficients with respect to the A and these are the P. And this is passed through the filter H and this is the G. So if you go for any frequency domain, Fourier domain concepts, if you are seeing H of omega square is a low pass filter, H omega plus pi is a high pass filter, and these are going to be given under ER QMF conditions, perfectly reconstructing quadrature mirror filter. So whatever I said that low pass and high pass like that. Fourier transforms. You may come across all these conditions. Okay, because repetitively for any band, it is going to be given as the variations is that finally you have to be get as a unit response. A uniform unity response as required. So based on this is derived in the frequency domain. So these are all the conditions has to be satisfied to give as a PR QMF requirements. And based on that filter Fourier domain, we are converted into an inverse Fourier transform. So based on this, we can define that a low pass filter impulse response h of n is orthogonal to even translates of itself, and high pass filter impulse response GL is orthogonal to even translates of itself, and h of n is orthogonal to G of n and its even translates. These are the required conditions to construct the filter band for DWT. So this is the requirement. Okay, this many times you may come across this diagram. So this diagram is coming from the equations. So apply the input. It is divided between G and H and decimated by 2 factors. Because when we are applying that, the scaling factor C of n, that summation must be going to be given as a integer value 2. Because of that, this sample is going to be come across. Okay, I defined in the 2 scale function pi of t. Pi of t is given as a coefficient C of n, pi of 2t minus n. So if you are integrate that and replace the rearrange the parameters, and that coefficient summation is must be going to be given as a 2. Because of that, it is going as a decimation by a 2. So if you go for in the next level, these are called as an approximate because it is passed through the low pass filter. So when we are considering a low pass filter, all the elements are passed through it as a low frequencies. So if you are observing the low frequencies, it is most approximate to the given signal, whereas G is a high pass filter. It is going to be talking about the edge transformations. Our eye is able to recognize the edge transformations more effectively compared to the common areas. If any variance is there, or I can say contrast variation is there, then only we can able to recognize that. So if you want to go for any further levels, take the approximate coefficients, go for the next levels. So this is an example how it is decomposed. So if you are saying the signal is first one, approximate coefficients, this is called as a Debeshev wavelet function. Based on this 4 is called as a detailed functions. Okay, if you are considered as a go for a first level decomposition, it is going to be given as a A1 and D1. A1 is again divided into D2, A2. A2 is divided into D3, A3. Then D4, A4. So this is final approximation is the four levels, and these are the detailed functions. So this will be called as a wavelet decomposition. So suppose if you have a noise signal is present, so noise is more disturbed like this type of the thing. Okay, because noise is also looks like this. So if you are filter properly this one, then we can able to filter more noise from this. If you say this is if you are passing through all these things in a one filter, all the components will going to be affected. So here a particular component if you want to subtract, you can able to subtract it. This is the advantage giving us a localization. So if you are able to give whatever the requirement filter cutoff frequencies is there, we can choose. So this we are going to be given as in a 4 components from the given function. So based on that, you can go for an filtering. By that, you can reduce in a low noise. That is the advantage of taking as in a wavelet transforms. So this is an example for denoising using wavelet transform. So original ECG signal is taken. So this is the ECG signal. This is a noise is added. Then denoise decay. So if you are go for that, mostly the coefficients, detailed coefficients or a high frequency components. Generally, the noise is mostly effective on the high frequency components. So filter that frequency, then it is going to be given as a original signal. So now we have to go for the image processing to apply the two-dimensional wavelet. Till now we have discussed this one-dimensional wavelet. So if you are go for a two-dimensional wavelet, I said the scaling factor phi of t. Now phi of t is expressed in terms of the two functions x and y. And this wavelet transform is valid whenever scaling functions must be as separable. Okay, if dependency is present in the x and y, we cannot apply these things. Okay, because we are said already that integral of two functions. So that integration must be integrable. Then only we can able to do it. So the first condition, if you want to apply the wavelet transform, whatever you are choosing the scaling function, it must be separable. In addition to whatever you are given the 4 conditions, which function has to be work as a scaling function. In addition to that, this has to be satisfied for a two-dimensional scaling function. So, and these are the relations between the wavelet function and the scaling functions. So, if you are having a components with respect to the scaling function, psi ij, horizontal component, vertical component, diagonal component, and phi ij is the approximate coefficients. Psi components, whatever is represented as related to the detailed coefficients. So these 4 functions is going to be used for the two-dimensional wavelet transform. So two-dimensional wavelet transform, we are considering that a phi of x, phi of y is represented as s of phi phi. Similarly, all things is phi psi and psi phi and psi psi like that. So if you use the theory is the same thing. Okay, function is expressed in terms of the coefficients a naught, ij, and the kernel, whatever is there, the scaling function we have to be substitute here. So like that, if you are see. So f minus 1 is the next level. We are approximating and go for the detailed function g naught xj, and just anyhow PPTs will be there. Just we will go through that. So we are going to be give as The components, if you are seeing, these are the components, 4 components. Okay, 1, 2, 3, 4. 4 components. You are simplify further. So if you are generating the sequence, there will be a 4 components is present. First one is A naught and B is obtained by first decimating the given coefficients A, I say, along its row with the L filter and then decimating the columns of the result with the same filter. So this is a LL filter, and the second sequence B naught and P is obtained by first decimating the input along its rows with an L filter and then decimating the columns with an H filter. And sequence of C naught and P is obtained by first decimating A LJ along with rows with H filter and then decimating the columns with the result L filter. Similarly, B naught NP is obtained by first decimating AIJ along its rows with the H filter and then decimating the columns of the result with the H filter. So that is in terms of the equation is given here. I'm not discussing that. So here the subspace is given with the W. So if you are consider that VK is the vector space, among of that these are the subspaces. So in the subspaces, whatever the wavelet coefficients is there, that is going to be belonging it. So if you are add all that subspaces, you are going to be given as a total vector space. So this is the fundamental final equation for the any function can be expressed in terms of this. This is the 2-dimensional DW. So this will be the requirement. Okay, you have taken as the input, passed through the filters, h of phi, h of psi, decimated. Again, this is divided. 2-dimensional, so we are going to be get as a 4 components. I already defined that. Phi component is the approximate coefficients, horizontal, vertical, diagonal. So this entire thing is going to be given as a decomposition analysis of the 2-dimensional filter, and this is the reconstruction synthesis. Exactly, we have to reconstruct from the 5 components, psi, 3 components, horizontal, vertical, and these 3 are the detailed coefficient. This is the approximate coefficients. 1 level, decomposition, and reconstruction. So basically, it has to be given in terms of a low pass filter, high pass and low pass, high pass, and high pass, high pass. So next level, if you want to go for this LL fit, is approximate coefficients is divided again LL2, HL2, LH2, HH2. A 2-dimensional representation to give as a decomposition. Just I given as how it will be. So this will be the result, okay, taken as the image at a different levels. Total is taken as the 4 subsections. This is again divided into a next level, again next level like that. Okay, approximate coefficients, and these are the detailed coefficients. Again from this it is divided. Again from this it is divided. Okay, and taken as the division at this place, remaining I keep it as it is. So this will be called as a image decomposition. So now we consider how this wavelet transform is work within an image fusion. Okay, not only for fusion, image wavelet transform already I given that noise reduction. Similarly, for image enhancement also we can use image compression also we can go for it. Anything we can apply on that. But best compression technique compared to DCT, this is also more or less meet the DCT but less than DCT. Okay, wavelet transforms can be applied for anywhere. So one of the application we can consider as an image fusion. So fundamentally, what is an image? Images are watching to produce a fused image with the best possible information we have to be. So this has to be produced a merged image with integration of information from more than one image. Analytical and visual image quality can be improved by integrating different images. So this is the why we have to go for fusion. You may come across types of the fusions. Maybe you are come across, then I'll skip it. Otherwise, I will explain it. It's maybe covered. No? So these are the different types how we have to be acquire the images and how to fuse it. And they broadly divided as it may not be said in this way. Just I will cover it. So low level image fusion, mid level image fusion, high level image fusion. Just I give the methodology how we are going to build. If you are say low level image fusion, it is a pixel level information. So if you are do combination based on the pixel level, then it is called as a low level image fusion. And in the mid level fusion, you have to be applied somewhat properties that is in a compressed, enhanced like that. So in terms of different characteristics, we are going to be doing the mid level image. On the image, take the characteristics of the image and do the process. That will be called as in a mid level image. And high level imaging is that you have to be take different things. Here I given as examples. If you are applying the Purdue logic, prediction, statistical information or a voting methodology, that is whatever is given, you are taking as the other attributes, not from the image characteristics as it is. You are taking as the other attributes. Based on that attributes, if you are do the process, that is called the high level image fusion. Okay. For example, low level image fusion, just you are applying the histogram, enhance it. That is a low level. Pixel by pixel localization if you are doing. Second level is that if you are taken as a certain compression methods, by that you are reducing the storing capability. On the image itself, you are taken as a certain characteristics. And third is that take other attributes. Major image processing example is the geometric images. Some of the characteristics are represented in the other terms, statistical properties. So if you are take as an entropy of that image, like that properties, if you are using, that is called as a high level. So basically, they are divided into these many types. So if you are considering image fusion, spatial domain, frequency domain, additionally now it is coming as a deep learning based functions. If you are considering a deep learning as a part of spatial or a frequency domain also, actually it is not a separate one, but still now it is considering it as a somewhat catching words. Because of that, it is taken as a other category. Otherwise, if you are applying the deep learning algorithms on the spatial domain or a frequency domain, that is also in it true. Fundamentally, we can say spatial domain and frequency domain only. Most probably, spatial domain may be covered by some other. I will give the comparison how it will be. So in the frequency domain, DCT is the fundamental image transform. It has to be applied on that. Other than that, there will be all remaining things are based on the wavelets only. Last one is called as a coordinate. We discuss only based on wavelets. 1, 2 methodologies we are going to be seeing. So this is the comparison. Just anyhow slides will be available. Just you go through it. Okay. Each and every method, how it will be, and what is the disadvantage of it. So for example, if you are seeing averaging, simple, okay, and easy to recognize and implement it. But the disadvantage is it is going to be finally decrease the image quality and reduces the noise into a final fused resultant image, produced blurred images not appropriate for real-time applications. That is in a very simple method. So this will be a frequency-based comparison. So in the frequency-based, I already given a some frequency domain method. It is Laplacian, Gaussian period, low-cost period, morphological parameter. These parameters are there. So it is going to be give us a better quality representation of multi-focused images, but the disadvantage is number of breakdown levels affect the image fusion results. So we compare the transform. Okay, if you are go for a discrete wavelet technique with the hard fusion, just you have to be choose a proper wavelet. So how you are effectively choosing the wavelet, your results is also changed based on that. So if you are choosing hard fusion, it produces a better quality of fused images with good SLR. This is very much useful with respect to the wavelet. If you are go for the compression wise, discrete cosine transform is a dominant one. If noise wise, if you are considered wavelet transform is a dominant one. And reduces the spectral distortion. Disadvantage is merged image has a fewer spatial resolutions. Okay, because we talking about more frequency resolutions, automatically time resolution is reduced. And this is the deep learning techniques, whatever is existing. That's the comparison. major drawback with deep learning is you require a large data set. Then only efficient results is going to be come. So finally, we have to be choose an appropriate, accurate, and reliable fusion technique is required for the various types of images for different domains that should be easily interpretable to obtain a better results. Whatever may be the technique, this is the fundamental requirement to apply any method. So this is the example how we are going to be using. This is one of the example that you are taken as the pan image, embed image, combining certain features from here and certain features from here, we are going to be get as the results. This is one type of the fusion technique, and the same technique, whatever previous thing is there, here it is taken as the two satellite images, pan image and this images. Whatever we are seeing the satellite images, it is not going to be get like that. It is going to be given as in a frequency band images. If you are seeing the raw satellite images, one of the color may be a dominant in one frequency band. Like that, if you construct any satellite image, it will require 8 bands of data. From 8 bands of frequency, different bands, we are going to be given as a color image. Okay, you will have to be combine all those images, then only you can get a final color image. So after combining all those things, only this image is coming. From here onwards, we are generally doing the process. So this in the medical purpose, you are going to be seeing as an MRI image and CT image, and if you are using that, it is going to be given as a good result. This is another type called as a camera and IR images. Nighttime vision is not there for digital camera. If you are combine those two, it is going to become that. So this will be a back focused image and force focused image. This is another type of diffusion. Till now, certain qualities of one image and other image is used it. This is called as a mosaic, is also called as diffusing. We are combining the parts. This image and this image combination is going to be your this image. Okay, we are not taking as the properties of this and properties of this combining. Entire two images is going to be added in certain way such that it has to be get this one. So this is also called as a one type of diffusion. So now we are going to be see how we have to be apply the wavelet transform for image fusion. So if you are taking wavelet transform, generally it is a powerful signal and image processing tool, and multi-resolution analysis has to be applied, and we have to be apply certain fusion rules. Apply the wavelet transform on the images and apply fusion rules. Fusion rules, how efficiently you are applying, based on that your results is going to be changed. So whatever fusion rules is there, that we are going to be applying after applying the wavelet transform. So DWT is the most useful multi-scale image fusion approach using the maximization selection rule. And if you are seeing the fusion, it is reduced cost and low storage requirement. So if you are seeing the wavelet transform, it is decomposed. So whatever the components, one image is decomposed into 4 parts. So which part you want to reduce it? So size automatically reduced to 1/4. By that we can say is low storage requirement is there. So generally it will be quantified in the existent mutual information NOP, standard deviation, line structure similarity index, spatial frequency. These are the certain measuring parameters, metrics. So this will be the methodology how we have to be apply the wavelet transform. So let's consider there will be any 2 images, image A, image B. Apply the wavelet transform. So it is going to be given as a decomposing. Choose which part you want. If you want the approximate coefficients, how many levels, based on that you have to be apply the fusion rule. And then combine that, you are going to be reconstruct. That is inverse wavelet transform has to be applied. Then you are going to be get as a fused image. This is the fundamental methodology to apply the wavelet transform. So here, advantages why we have to be go for the wavelet transform is that one is the locality. That is, information of image is represented by wavelet coefficients, which is local in space and frequency. Already it is divided as in a horizontal component, vertical component like that. So which component you are going to be processed, that will be affect only that component. It is not going to be disturb the other components. That is the meaning of the locality. And multi-resolution analysis is image can be represented at a different scales. So example, if you are consider the locality is for fusion, you can apply the fusion rule locally and that would not affect the other portions of the image. So multi-resolution analysis, let's talk about that. Producing fused images at a multiple levels. Higher the scale is the more the detailed information is captured from the source images to fuse with the image. Shortened filter bands of the wavelet decomposition are useful for it and works well for image fusion. So how efficiently you are going to be take as the filter cutoff frequencies, all those things, it is going to be give that. So another advantage is that edge detection. So wavelet transforms is, you already said that it is acts as a local edge detectors because HH frequency components is present. So if you preserve HH and reduce the low frequency noise, then sharpness is going to be increased in the fused images. Fusing rule is a different, okay, whether you are applying the wavelet transform or not, fusion rule will be there. So based on that rule only you are fusing. In addition to that, if you are applying the wavelet transform, it is going to be give that. So we can able to preserve the edge. So the quality of the image is going to be present once you, even though you are applying the fusion rules. So this three-dimensional edges is present. You can able to separate these three vertical, horizontal, and diagonal elements is present. Those are called as an edges. Then decorrelation is that most of the wavelet coefficients of an image tend to approximately decorrelated. So whenever we are dividing, decomposing, LL components is different from HL, LH, and HS. So that is the meaning of the decorrelation. Generally, if you take any data, plus or minus 32 points, 32 times or 32 levels dependency is there. Any one of this element is disturbed or processed, it is going to be effect on the other elements. So if you are consider any signal, it is continuous only, even though we are saying a digital computation discrete, it has to be transmit like a pulse or a wave. Once we say pulse and a wave, there will be a dependency between of the present and future, whatever is existing levels. So that levels we have to be considered at least plus or minus 32 points. So that dependency is always there. Certain extent we can able to reduce if you are apply the wavelet transform. Then energy compaction is we already saying that compressed images. So if you are apply compression easily, if you are say that high and high frequency components are there, from that you can go for any range of the pixel values is available. So dynamic range is going to be reduced if you are reducing high and high components. So you can easily find the range in the 4 levels. According to that, you can choose the required level of the reduction of energy. So if you go for edge detection, this property helps in preserving the edges and implementation of edge sensitive fusion methods. And if the decorrelation is thus during the fusion process, if there is some change in wavelet coefficients, then generally this would not affect the other portions of the image. This allows applying a fusion rule on selected wavelet coefficients without affecting the other parts of the image. And this property facilitates the implementation of energy-based fusion rules, which preserve the silent features of the image. So this is the advantages if you are applying the wavelet domain. So now one example, we will go for the medical image fusion. So consider the different available medical images. X-rays is widely used to detect features and abnormalities in the bone position. CT scans are used in tumors and anatomical detection. And MRI is used to obtain information about tissues. Images. So if you are combined one or two combinations of these things, it is going to be given as a more detailed images. So if you are see that generally so much of research is required in this field. Okay, I did in the medical image processing is the lung cancer. Lung cancer, on that we worked a lot of even my papers also more is covered on the lung cancer and brain tumor. On brain tumor, so many is worked, but still there is a need. So if you are considering MRI scan, CT scan, even though they are the new technology or a technique, still 60% of accuracy is available with respect to those images. further you can process it. Even though literature is saying that accurate values is 90%, 80%, algorithm wise, mathematically, we can say that, but no instrument is giving more than 60% of accuracy. So still there is a requirement. If you do certain algorithms develop up to an instrument level, that is in a very advantageous. So if you are design some certain chip design, add to the MRE scan machine, it is in a very much useful. And another research field is that light, whatever your AC supply 50 hertz, it is very much disturbing the signals, because almost all body organs, whatever blood velocities is there or any heartbeats is there, it is more or near to the 50 hertz of the signal. So any slight fluctuation, but I not able to observe in the light AC supply is coming nearby this instrument, it is going to be disturbing it very much high. And noise wise, if you are consider that, generally whatever algorithms is available, added noise removal is only present. Still, this is also added noise only we are removing. But practically, it is not at all an added noise. It is a multiplicative noise. So most of the instruments is going to be given as a speckle noise. So multiplicative noise analysis, if you are able to do, that is in a very advantageous to reduce this type of the instruments. So this is the one of the method. So let's consider I1 and I2 are the two source medical images. First, we have to be applied. That is, we have to be decompose these two signal images. So apply I1 is a W1. I am indicating L is levels. Okay, after dividing a certain levels, it may come at the convergence. At that point, you will leave it. Okay, it is not necessary that level 4 may be given as a good improvement compared to the level 2. It is not like that. At any level, depending on your requirement, it is going to be due the improvements. Not always increasing the levels is going to be improve the quality. It may not be. So first, we have to apply the DWT on these two images. Then calculate the fused wavelet coefficients at a scale L by following the expressions. I am taken as a simple rule for the fusion. Here I am taken as that if the magnitude of W1 LXY is greater than or equal to W2 LXY, then it will be written as a W1 XY. Pixel wise only I am given this rule. Okay. Images I will show. Okay. In the MATLAB only it is implemented. Now everybody is writing in Python. Okay. Whatever maybe you can do it. So this is the condition that taken as pixel by pixel comparison only. Applied the wavelet transform. This resultant images we are compared. So which one is higher? We are returned that. Okay. Value of pixel, which one is higher? I returned that. Here this rule is assumed that images whatever is expired is a dark part is more. If you are taken as a high intensity images and apply this rule, it will not work. Okay, it's going to be given as a more brightened. So dark images is going to be work if you are applied the fusion rule. Then reconstruct the fused image at a scale L using the inverse DWT. This is an inverse DWT of whatever here you are applied image is there. It's a very much simple fusion rule. Apply the wavelet transform on the images, apply certain fusion rule, then inverse it. Okay, this is one of the simple algorithms to give as a fusion of the two images, and it is applied on the medical images. So if you are consider this CT images, adjust structure MRI. So this is an MRI and CT images. By combining these two images at a different levels, these are the fused image. We have taken as a 2 to 8 levels. If you are observed that I didn't taken this as you are apply the qualitative image, you can observe it. Okay. By visualization, I'm not able to find any difference. Even the cut and paste like this one. So it's a very difficult to observe which one will improve a lot. So if you are opening a quantitative image values, these are okay, different metrics I don't know. So QI, MIB, SD, DSSIM, SF, and AG. So if you are calculated this, level 2 is, if you are observed that there is a no much difference is present, 0.72 at level 6, it is giving us the same parameters. Almost it is given as an same. If you go for a 3, 4, 5 digits, then there is a slight difference is there. Okay. And this table I didn't has not covered in the one slide. So I taken as up to a 2 digits only. But whenever we are doing, we have to be go further digits. 4, 5 digits has to be given. Then only you can observe certain change. So this will be the parameter metrics till now whatever is using. Then a simple fusing tool, we are added that and we are given as in more details in the image. So if you are observing that, you are going to be given us, see, it is looking more or less like this, but if you are observed, particularly the edges is enhanced compared to this. If you are seeing here, just see these two, it is going to be given as a slightly brightened, and here details is more if you are compared to here. Here we are not able to give any detail here. So at this point, if you are observed, certain details is present. Okay, still it is not improved much, but you can able to give us a certain details. If you assign some colors, then it is going to be give us a more clarity. So this is another image taken as on the brain. T1 MRA and this is a MRA. These also from 2 to 8 levels. If you are observed here, these two are combined. So this edges is here is preserved, and this small details, if you are observed, this small details is enhanced with respect to it. If you are observing this, see if you are observed contrast is here reduced more. Is taken as the same fusion rule only. Whatever is applied previous case, the same fusion rule is applied. So if you consider the previous image, somewhat it is improved. If you see here, it is not lost. If the levels is increased, here it is more or less giving us a same look. So when the same rule is applied here, it is going to be given. It is see this is more or near towards this one. But whenever you are observing here, the edges is preserved a very brighten, and whatever bright parts is there, they are preserved because I said that no condition is that only. Whichever is higher, I retained that only. So if you are observed that go on increasing, whatever the higher intensity parts is there, they are retained here. So if you depending on that, which level you want the result, you have to be keep that and do the further process. Same rule is applied in both. So previous case, it is in a dark image. So whatever we are taken as a brighten, it is not affect much. It is looking a light. Wherever we are going on that, if you are compared these two, go on increasing the brighten levels. So if you are observed here, go on dominating this one. Okay, if you are increasing the levels, these parts is more brighten compared to here because of that it is more similar to these parts. So if you are observing this edge, this is a more brighten. So that brighten is retained here, and this parts, whatever this dots is indicated, that are more brighten. So it is coming dark. So this is another example. Same vector image only. So next is another method taking as that a gradient. So here we have taken as AXY and BXY with the two images which has to be fused. Apply the wavelet transform. Then here I'm decomposed into low frequency and high frequency. Previously, entire taken as a low frequency subimage and high frequency subimage and indicating with these letters. So now apply the gradient images on these low frequency and high frequency images. So now here the fused rules is taken the G, that is gradient of this image is greater than the gradient of the B image. Then the fusion image is called as a high frequency of these components to establish the high frequency component. Similarly, if it is a less than high frequency components of D. Dividing the wavelet transform advantage is utilized here, taking the high frequency and low frequency components. So high frequency components is in the image A is higher, I'm returning that. If the B have a high frequency component, I am returning that. So finally, in the fused image, all high frequency components is getting. Similarly, for a low frequency components, here I'm just like that. I'm not taking as which one is a low one. So I am giving as a low frequency is this added equation because if you are considered as a low frequency components, if I go for that, any image, if you are observed, low frequency components are nearer to the original image. LL image, if you are observed, it is very much near to the original one. So we cannot lose that low frequency components. Because of that, I'm adding those two. Okay, just simply I'm say that which one having a very low frequencies, if you are retain that, most of the information you may lose. Because of that only the reconstructing also we are taken as a low frequency components as it is, then add at other level, whatever is getting, we have to be divide from that low frequencies and add it. So under that I'm taken as in a different way. This is a combination of those two frequencies. Low frequencies from the two images. So image P is fused into the image A, then K1 is greater than K2. This is the certain constants, and you can change the values of K1 and K2 to get as a proper fusion. So this will be the way to be given the results if you have observed. This is the original image with the resolution 20 meters is taken. Average gradient for this image is 4.78. Average gradient of this image is 12.33. So original image, this BX5 is with a resolution of 10 meters. If you are using these two, it is going to be given as this resulted with a gradient of 11.16. Higher gradient, if you are see, here we are using as a low frequency components. Gradient is edge. Changing from one level to the other level is finding in the gray. So the gradient, if you are observed here, compared to these edges are lost. If you are seeing the color combination also, okay. So this high frequencies or maybe any frequency may represent these colors. So that combinations is going to be given with an fused image of 11.16. So most of the higher frequency components are present here. Low frequency components are present here. Low gradient is going to be talk about low frequencies, that is changes, not actually the entire area. It is changing from one pixel to the other pixel or one region to the other region. Is less in this one, it is high in this one. Because of that, we are visualizing more in this image compared to this image. But wherever constant areas, if you are observed, here constant areas we are not able to view, not able to identify. So if you are seeing, this is very lightly we are observing, here it is different color. We can take this as we are observing it. So when we are combining, this area is getting as a clear. That is the meaning. Okay, gradients, if you are go, edges is going to be prism. From one region to other region, changes is more from point to point, then gradient is going to be get as a more. So this will be a reasonable visibility is given with respect to the based on the gradient rules. These are the differences. I just given as an image fusion with respect to the certain results and wavelet series. So many are there. Okay. So if you have any questions, you can ask. Contour, let's see. That is going to be taken as, suppose I'm taking as this edges is there, right? So we have to be represent this as like a contour. Edges. Most probably in the contour and lines. Line, if you say line equation, if you are using, line will be circle, square, like that. Irregular shapes also we can represent. Fundamentally, they are going to be given as the differences. Let's say, suppose if you are taking as an image, and if you are taken as 1 point, let's say that is a D1. And line is going to be given, edge line is going to be you that. And you are go and scan it. Then next where it is ending, distance between these two is calculated and represent that as a curve. So like that, all will be done. So for that, you have in a certain like function has to be represented. So mostly curvelets is not getting as a more efficient result compared to wavelet, but wherever like this type of clippings is there. If you are fine for that type of clippings, curvelet works well. We are not using computer. We can use it. This is depending upon which part you want to use it. Suppose we have to be written like bulge. Okay, if you are go for any kill birds, like that things is required. Suppose in a satellite images, geographical images, at that part, curvelets is works well. Contour is a different again. Wavelet is a different, contour is a. And you may come across a Gabor transforms, right? They are more or less like a short wavelet, short Fourier transform wavelets. So if you are combined the short Fourier transform with an irregular shape of the windows, then we can call that as an contour lens. That one I'm saying contour. Irregular shapes. Then we go for a contours. But it is a very difficult, no, we cannot estimate or we cannot automation, we cannot do it. If any mathematical expression is there, then only we can able to give as a automation. So like that type of things, it is a very difficult, but algorithms is available. Contour algorithms is available. So any regular shape is there, we apply that algorithm. So it is try to bring it to the more nearer shapes. Even snake algorithm is also there. So most of the image processing points of view, we want to detect a certain requirement. So that may be an irregular shape. Example, tumors. So tumors, under the assumption how we are doing is that most of the times tumors are near circles. It may not be a circle, right? So for that time, contour wavelets, the contour transforms is very much useful. So we are applied. Snake algorithm is there, contour algorithms is there. So any irregular shape, we have to be go nearer to that. So for that, one example is that like fusion rules, we have to be give as a rule in such a way that tumor and other parts. So tumor, how much intensity is going to be due. Only the disturbance if you are go for a tumors is blood vessels. Blood vessels have a high intensity, tumors is also high intensity. Depending on type of the tumor also, because tumor in the sense it is just like a proteins. Proteins is added like a combined one. So it is also gives as a high intensity, whereas blood vessel is there, it is also given as a high intensity. But blood vessels, you have to be find out the small tumors. Suppose a tumor is this much up there, it is identified whatever cancer is present. So it is in a very thin, then only we can able to do it. So like that type of the thing you want to find out, it has to be differentiated, especially from the blood vessels. Blood vessel may not be much size. It's go on distributing it. Any node may contain a certain amount of size. It's a lot of confusion between these two is there. Till we are not able to identify finally or differentiate these two things. So in that time, we have to be find out a contour wavelet transforms. So it is going to be find a very near region, finding that high intensity and other thing we assume that it is a low intensity. Comparing that and get nearer to the high intensity value. So by calculating the energy of the segmented part, other part, if you are go on merging like that, it is going to be find the shape of the tubes. Okay, that type of the things we already done. Time is there, I can show. I think in PPT it may be there. Okay, we will start here. Is there any questions?
Thank you, ma'am. This is Rakesh, Assistant Professor, EC Department. I give a word of thanks to ma'am briefing on different concept, discrete wavelet transform, and introduced with very basics and also discussed on different equations behind this discrete wavelet transform, and discussed on noise reduction, how to overcome the noise in the wavelet transforms, and applying this discrete wavelet transform in the image fusion and extended for medical applications, how this DWT is applied to fuse the images. So I thank you, ma'am, for within a short time discussing on different aspects of using DWT in medical field. Thank you.
The token of gratitude from Madam. Yeah.